Throughout history, our biggest leaps in technology have occurred as a result of new materials becoming available. I've shown you how it took humankind centuries to master iron and steel, culminating in the explosion and growth during the Industrial Revolution. How the accidental discovery of age hardening allowed aluminium to take humans into the stratosphere in droves, and how silicon forms the backbone of this age of information. But today, we're going to discover the next great leap in material science: carbon fiber reinforced plastics. Carbon fiber, and its even more futuristic brother, carbon nanotubes, have been touted as the next great innovation that will allow humans to build amazing structures that were once unimaginable. Elon Musk recently revealed an enormous carbon fiber reinforced plastic cryogenic fuel tank, the largest fuel tank that has ever been created for space flight. Building spaceships of this size is not an easy task. The larger the spaceship, the more fuel you need to escape the Earth's gravity. The more fuel you need, the bigger the fuel tank needs to be to hold it, which just adds more mass to the rocket. Carbon fiber reinforced plastics provided a new way to keep the weight down while maintaining the strength needed to withstand the internal pressures. But building a structure like this from carbon fiber is no easy task. This is the sort of material that, if a crash landed on Earth just 70 years ago, it would have been a completely alien object, and we are still learning a lot about its mechanics. The fact SpaceX have created a structure this size out of carbon fiber reinforced plastics that has already been tested at 2/3 of its bursting pressure is astounding by itself, but we've yet to see whether it can resist the blistering cold temperatures of the liquid fuels without cracking and leaking, and do it repeatedly. After all, the whole point of SpaceX rockets is to be reusable. Building a cryotank out of composite materials is without a doubt the most difficult part of building a spaceship of this size. Don't believe me? Listen to the man himself say it.
This is really the hardest part of the spaceship. The other pieces are we have a pretty good handle on, but this was the trickiest one, so we wanted to tackle it first.
Nevertheless, the material will be pivotal in reducing the weight of our craft enough to escape the gravity prison that has kept humans as a single planet species. Even though we are still learning a lot about the material, carbon fibers by themselves are not as new as you may think. The first carbon fibers were produced by Thomas Edison and Joseph Swan for use as filaments in their new electric incandescent lamps. The carbon fibers they created were produced by carbonizing plant threads like cotton, wood, and bamboo. This material did not have the tensile strength of today's carbon fibers, but they allowed Edison and Swan to replace the expensive platinum filaments being used earlier. The carbon bamboo filaments Edison developed lasted up to 1,200 hours, and they were the norm for 10 years until tungsten filaments replaced them. Not much thought was put into carbon fiber as a structural material until the late 1950s, when the Union Carbide Corporation, a company that manufactured light bulb filaments, began investigating replacements for tungsten filaments. They started using rayon, an artificial cellulose-based material, popular as a cheap alternative to silk and cotton as the base ingredient for carbon fibers. This was a breakthrough moment for the start of the modern carbon fiber era, as the resulting material showed potential as a structural material. Researchers all over the world took notice, and just a month later, the Japanese Industrial Research Institute began investigating how to make their own fibers from polyacrylonitrile, or PAN for short. The majority of today's carbon fiber is produced with PAN, even though it is an expensive byproduct of oil production. It yields a fiber with a much higher percentage of carbon than rayon, and it's easier to manufacture. Dr. Shindo created long strands of this PAN material, which he stabilized by first heating it to around 250 degrees for up to 2 hours. This rearranges the chemical bonding to create a thermally stable ladder bonding. These fibers were then heated again to around 1000 degrees in the absence of oxygen, which expels the non-carbon atoms in the material, leaving tightly bonded carbon atoms arranged mostly in the direction of the fiber. This material was both heat and chemical resistant. It had fantastic tensile strength and didn't rust. Specialized industries like aerospace immediately saw its potential to help spacecraft break the grip of Earth's gravity, and when Gabe Brewer won the Tejeo Club Masters golf tournament in 1972 using a carbon fiber composite shaft, the material captured the world's attention too. Sporting goods manufacturers all over the world began creating carbon fiber products. Golf clubs, tennis rackets, and racing bikes started to be made with the cheaper off-spec fibers that the aerospace industry could not use. Despite its high price, demand for the material kept growing, and by 1980, 1,000 metric tons were being produced a year. But it was still a notoriously difficult material to work with, and many still doubted its ability as a structural material. During the development of the McLaren MP41, one skeptical engineer is said to have picked up a piece of carbon fibre composite, just like this, and easily snapped it in half, declaring that the material was too weak and brittle to be used for the ambitious carbon fibre composite monocoque. But he was breaking the material across the fibres. If he had attempted to break it along the fibres, he would have had serious difficulty. You see, carbon fibre is made from these tiny thin fibres. This is a picture showing the size difference between a carbon fibre and a human hair. The carbon fibre is a smaller one. These tiny fibres by themselves can't be used as a material. We first have to bind these long strands of fibre together with a plastic resin. Otherwise, they're just a flimsy fabric that can't hold any load other than tension. Here you can see a solid piece of carbon fibre, where the fibres are surrounded by white resin. But this technique causes some problems for engineers when designing a product with this material, because the plastic is weaker than the fibres. This is a unidirectional layer of carbon fibre held together with resin. If we pull it this way, along the fibres, it has fantastic strength, because the fibres are in the same direction as the load and thus can resist it. But if we pull it this way, there is no continuous run of fibres to resist the force. Instead, the resin matrix gets pulled apart, and the fibres add very little strength to the material. To combat this, engineers will layer the fibres on top of each other. Here we have a 0-degree layer on top of a 90-degree layer, so the material properties are the same in those directions. But now the 45-degree direction is weaker. We can keep adding more layers until we have similar stiffness in all directions, but eventually the thickness of the material will become too great. We reach another problem when we remember there is nothing but the resin matrix holding these layers together, and sometimes that fails and we get delamination of the layers. This is why you often see the carbon fibres woven into a fabric like this, but again, woven fabrics can only be so thick. We also need to worry about the drapability of the material, as these fabrics need to be shaped over moulds, and a very thick material like this can make that job very difficult. These issues create a whole lot of work for engineers working with composites. But with experience, we have learned to use these unique material characteristics to our advantage. The designers of the MP41 managed to create such a strong monocoque with the material that when the car did crash, it silenced many of its doubters. We can tailor the fibre directions to optimize the material properties. Here we performed a tensile test on a tiny piece of carbon fibre composite with fibres only in the direction of the force, creating an incredibly rigid structure that barely deformed through the test and managed to hold 5.3 tons before breaking. But stiffness like that is not always desired. For example, in the event of a crash, you want your car to crumble and deform to absorb as much energy as possible. And so composite noses of F1 cars are designed to fragment into millions of tiny bits, and this helps absorb energy and decelerate the car more slowly. Pressure vessels like the Dreamliner fuselage are wrapped in layer after layer of resin-soaked carbon fibre by a robot that places it in the exact right position, making the structure perfect for withstanding internal pressure. One of the big problems when building a structure this big with composite is that they need to be placed in an autoclave to get the best quality material. An autoclave applies heat and pressure to the material to set the resin and forces the air and other voids that weaken the material out of the resin during the curing process. The autoclave Boeing uses for the Dreamliner is massive, and there isn't an autoclave in the world big enough to fit the tank SpaceX created. It's hard to know how they did it, but they almost certainly used an automated tape placement robot, like the one Boeing used to create their own smaller cryotanks, which can cure the resin with a laser as it lays the pre-preg carbon fibre tape down. But it's very hard to create quality parts with this method, as the pressure of the autoclave is essential for removing voids in the resin. And this is such a huge concern for composite manufacturers that parts are often scanned with ultrasound technology to check that the resin has cured with a tolerable amount of microvoids. This machine sends ultrasound into the part through a jet of water and detects the voids in the material. These voids are an even bigger concern for this application, because the biggest problem for the material is cryogenic fuel leaking through microcracks and voids. Looking at the outside of the tank, I would say with a fair bit of certainty that the tank was made in two halves that could fit in an autoclave, and was then riveted and welded together, which I would imagine will be removed for the final version, as this just creates weakness in the structure. But this is all guesswork. Breaking news! Yeah! So while I was making this video, pictures were posted to the SpaceX subreddit by user DeathCogUnit, showing the remains of the cryotank after being tested. It failed exactly where I said it was going to fail, but SpaceX have yet to make a formal announcement about the results of this new test. This does not mean failure of the project. We test things to learn more, and it's fantastic that SpaceX are pushing the boundaries of what is possible. I still have so many questions about how this thing was made, which just makes it more frustrating that all the questions being asked in the Q&A session after the big reveal were so stupid. This advancement, if we can make it work, will be the most significant leap in rocket technology we've seen in recent memory. Boeing stated that their cryotank provided a 40% weight savings over traditional aluminium fuel tanks. That is going to allow us to launch larger vehicles into orbit, reach further into our solar system, and hopefully, not in the too distant future, it will help humans become a multi-planetary species. Thanks for watching. This episode is once again brought to you by Squarespace, who have helped me make my next move with my website. In my last video, I revealed I was working on building a site that would continue my mission of sharing the amazing engineering that surrounds us in our daily lives. And this week I can announce that the site is finally live at www.realengineering.net, and it's looking great thanks to Squarespace. Squarespace allows you to create a beautiful website or online store with award-winning templates. They have 24/7 customer service, and their intuitive design platform makes it easy to create the website you dreamed of. You can make your next move with Squarespace too, and build a beautiful website by using the code REALENGINEERING for 10% off your next purchase. Thank you Squarespace for helping Real Engineering exist both here, on YouTube, and on our beautiful new website. If you'd like to follow our progress as we build this site, please sign up to the newsletter on the site. And thank you to all my viewers and Patreon supporters too. I'm close to making my first hire for this channel to make more of the content that you love. If you'd like to support Real Engineering, please consider supporting us on Patreon, or maybe even buy the new Real Engineering t-shirt, which is available as a $20 reward on Patreon or over on dftba.com. If you'd like to see more from me, the links for my Patreon, Facebook, Twitter, and Instagram accounts are in the description.